Okay, welcome to example number 6. Now before we get into example 6, I just wanted to review a few topics, and particularly how does the charge distribute it around a conductor, and furthermore, what does the equal potential and electric field lines look around these differently shaped objects. So a number of experiments were performed by Michael Faraday, and I wanted to just reiterate some of these important points that are shown down here in the diagrams. First of all, under electrostatic equilibrium, that's basically when the charges are stationary, we find that when the charges are all repelling each other and finally come to at rest, then you'll find that on a regularly shaped object these charges will all be evenly spread out. However, if you look at an irregularly shaped object, you'll notice that there's more charges here around this greater curvature here, and you'll notice the electric field lines are all equally spaced, but right around here you have to have the electric fields going around a greater curvature, and hence all these charges over here will be greater, and so that's why you'll have more charge accumulating over this sharper point, and that's why typically you'll get discharges that occur at these sharper curvature points. The surface of the conductor here and here are basically what we call equal potential surfaces. That means the potential at A and the potential B are the same, or the potential here or here are the same. There is no potential difference between any two points along the surface. We're going to be discussing also that inside the surface in a moment, that if I were to put a point C here and a point D here, that these 2 points will also have the same potential as well, and so there is no potential difference between C and D, and I'll get to that point in a bit. The electric field lines, if you notice, are perpendicular to the surface. At every point to the surface they're always perpendicular, because if you recall, the electric field lines and the equal potential lines are always mutually perpendicular to one another. And of course, electric field lines always leave the positive and go towards the negative. So if this had been negatively charged, then these electric field lines would be going towards the surface. Alright, now let's go on to skip ahead in 2 pages from here. Okay, so now I've moved over to this page where we're discussing the electric potential and the electric field of a charged spherical conductor. Okay, whether it is solid or hollow, we're going to get the same situation. And what I wanted to review is that inside the conductor, the electric field is 0. And we learned that back in the last chapter, but maybe you've forgotten. You have to remember that under static equilibrium, these positive charges, or whether it's negative charges, would all repel each other. They would be all found on the outside surface. And when we talk about equilibrium, we're talking about charges not moving anymore. So that means that all the excess amount of charge is now located on the outside. So that would basically mean that if you were to put a charge in here and it were suddenly starting to move, then it would no longer be under equilibrium. So remember again, all the excess amount of charge is on the outside. So inside there is actually no net charge. The Q inside, basically, Q inside is 0. It doesn't mean that there are no charges there. It just means that there are just as many protons as there are electrons. So the net charge Q is 0. So now this is an important thing that deals with potential, because the electric potential inside the surface is not 0. It's actually constant, and I want to reiterate why it's constant inside the sphere from 0 to r. So this is the radius of the sphere. If you recall from earlier, we talked about the electric field was called the potential gradient, which is the change in potential over the displacement. And if we consider E, that is inside, if E inside is 0, then basically delta V inside must be 0. That doesn't mean that the potential is 0 inside. It means the potential between 2 particular points. So if I were to sort of draw some kind of conductor here, and if I were to look at 2 points, say 1 and 2 here, and I were to move along this particular point, then the potential at 1 must be the same as potential at 2. So there would be no work done in moving the charge from here to here. Now, if the charges were suddenly had to move, then that would be, we're no longer under equilibrium. So the potential all within the sphere is exactly the same as what it is right on the surface of the sphere, which is called an equal potential surface. So how do we calculate the potential inside the sphere and right at the surface? We use the formula KQ over R. So this is equal to K Q all over capital R, just because I want to reiterate that as R represents the radius. Now the potential, I should have actually wrote here where R, little r represents capital R. However, inside the sphere, remember that the electric field is 0 here. And as soon as you pop out right out to the outside, that's where you have your strongest electric field. And then, of course, as you move outside for both of them, both the electric potential dies out to 1 over r, and the electric field will die out to 1 over r squared, so that when r approaches infinity, both electric field and potential will be 0. So now let's move on to example 6. You can also, by the way, look over here at this little potential graph for gravity, and that will help you understand it as well. So let's go on to example 6. That's what this video tutorial is about. So move down to the bottom of the page. Okay, so here's example 6. We have a conducting sphere with positive charges all out on the outside sphere because it's in equilibrium. We're asked to determine the electric potential and the electric field at the surface of the sphere, so let's go ahead and do that. So at the surface, the electric potential will be calculated by using KQ all over R. So that would be 9 to the power 9 Newton meter squared per Coulomb squared. Q is 5 to the power negative 6 coulombs all over the radius of the sphere, which is 9 meters. And the electric field at the surface would be calculated in a similar way, except you would have KQ all over R squared, and that would be 9 to the power 9 Newton meter squared per Coulomb squared, multiplied by 5 to the power negative 6 coulombs, but now over 9 meters squared. So go ahead and calculate both of these and see what you get. And for the first one, you'll get a voltage of 5,000 volts. And the electric field at the surface will be outwards at 556 volts per meter, or newtons per coulomb. So now let's go ahead and calculate the potential inside. Now if you recall, the potential inside the sphere, anywhere in here, is going to be the same as the potential at the surface. So we don't really need to go ahead and do this calculation over. We know it's already 5,000 volts, so let's just write that down as 5,000 volts. And the electric field inside the sphere is going to be 0 volts per meter because there is no electric field inside. Remember that if there was an electric field, then suddenly these charges would be moving, and then you would no longer have electrostatic equilibrium. Okay, so now let's go on to part C and determine what the electric field is at some point where it's 12 meters from the center. So E at that particular point and V at that particular point. So E would be KQ all over R squared, and V would be KQ all over R. Let me just fix that. That should be actually R. Okay, and that's because that's representing the distance from the center of the sphere to this 12 meter mark. So we put in K, which is 9 to the power of 9 Newton meter squared all over Coulomb squared, times Q, 5 to the power of negative 6 coulombs all over the distance of 12 meters squared. And then similarly for potential will be 9 to the power 9 Newton meters squared per Coulomb squared, times 5 to the power negative 6 coulombs divided by just 12 meters. And so you can go ahead and put that in your calculator, and you'll find that the electric field is now 312.5 volts per meter, so it's weaker than it was before, and the voltage will be 3,750 volts per meter. Oops, that's just volts. And then we now basically finished the problem. But I think what make sure you also understand is make sure that you know the graphs. So you should draw graphs for both of them. So here I'll go ahead and produce the graphs. And so what we'll see is the electric field inside is 0. So along here is 0 until we get to that just to the outside surface, and then it pops out to its maximum value, which is 556 volts per meter. And then as R approaches infinity, so then it dies out, dies out, dies out. In fact, E is inversely proportional to R squared. And if we were to calculate R at 12 meters, this value here would be basically around 312.5 volts per meter. The voltage, a little bit different story here. Remember that inside the sphere the voltage is constant. So we'll start off with a constant voltage of 5,000 volts. So here's 5,000 volts, and it's going to remain constant roughly until you basically get to this radius just at the outside surface. And as soon as you start to get off that surface and move outside, then R dies out as well. But now you'll notice that here the voltage is inversely proportional to R. This is an inverse curve. It doesn't quite look like it, but it should be an inverse curve, whereas this is an inverse square curve. You should know these two graphs for a electrical conductor, so don't forget to know these, and notice that again the equipotential is constant inside the sphere, whereas the electric field is 0 inside that sphere. Okay, and that's it for example number 6.